Welcome back to the deep dive. I have a question to kick things off, and I need you to be honest.
Okay, I'm ready.
Do you have a lucky item of clothing, like a specific jersey or, I don't know, a pair of socks that you were just convinced helps your team win?
It's funny you asked that. I mean, I like to think I'm a pretty rational person,
What?
but I have this one coffee mug, and I swear if I don't use it on a day when I have a big meeting, that meeting just goes completely off the rails.
See, everybody does it. I have this lucky hat, and, my logical brain knows that the cotton fibers on my head have absolutely zero impact on a football game happening 3 states away.
But your gut tells you something different.
My gut says, don't you dare take that hat off.
And that's the human brain just doing what it's best at, is connecting dots. We see two things. I wear the hat, the team wins, and we just invent a causal bridge between them. We crave it.
Today, though, we're going to try to shut that part of our brain off, or at least learn how to fact-check it.
We're digging into a fantastic set of lecture materials from Dr. Beags on inferential statistics.
And this is part one of a two-parter we're doing.
Yeah.
The mission here is, I think, pretty cool. We're looking at the toolkit scientists use to go from, I have a gut feeling this works, to
I have mathematical proof that it works.
we're cracking the code of causality, the science of better.
We're jumping straight into a study by Dr. Beags. This is really foundational stuff. The big question is, do enriched environments actually influence cognitive ability?
So, in plain English, does having a fun life make you smarter?
Essentially, yeah. So Dr. Beags starts with a theory. The theory is that environmental enrichment increases brain plasticity.
But a theory is too big, it's too fluffy, you can't test it directly.
You can't. You have to boil it down into a testable hypothesis, a specific prediction.
And that hypothesis was that mice raised in these enriched environments would be better at a maze test than mice from standard, boring lab cages.
And when we say enrich, we really mean Mouse Disneyland. They had wheels, toys, all sorts of nesting materials, tunnels.
And the other group.
It's just the basics. Food, water, bedding. That's it.
Okay, so she runs the experiment. She waits till they're 8 weeks old and then measures how long it takes them to find food in a maze and what happened.
The results were really clear. The mice from the fun cage, the Mouse Disneyland group, were statistically significantly faster.
So the toys worked. Case closed.
Well, hang on. This is where we have to be good scientists, right?
Yeah.
We have to be skeptical. How do we know the toys caused it?
What else could it be?
What if Dr. Beags, maybe without even realizing it, put all the naturally faster mice in the fun cage to begin with?
That would be cheating.
It would be bad science. And that's why the most important term, probably in this entire deep dive, is random assignment.
We hear that phrase all the time, a randomized control trial. Why is that the magic wand of science?
Because it just destroys bias. If you randomly assign them, it means the only systematic difference between Group A and Group B is the one thing you're testing.
The environment, the toys.
Precisely. So if you see a difference at the end, it really has to be because of the toys.
So Dr. Beags uses this study to check off the 3 big requirements for saying something causes something else.
Exactly. First up is covariance.
Which is just, did the result change when the cause changed?
Yep. Better cage, faster time. Check. Second, temporal precedence.
The timeline, right? Did the cause come before the effect?
It has to. They lived in the cage for weeks before they ever saw the maze. Check.
And the third one is internal validity. This is what random assignment gets us, isn't it?
That's the one. It rules out all the other explanations. It wasn't just better genes, it wasn't different food, it was the toys.
There is a fourth one mentioned in the slides, though. External validity.
Ah, yeah. This is the one that keeps scientists up at night.
What is it?
It's the question of generalizing. So, okay, we know this result is true for these specific mice in this specific lab, but does it apply to all mice? Does it apply to rats?
Those apply to us.
Exactly. Does this mean if you buy a treadmill, your IQ goes up? The study suggests it's possible, but it doesn't prove it. That's the leap.
Okay, so that's the slow, careful, scientific way.
Yeah.
But in the real world, we don't do that. We just see things. I drink some tea, my cold goes away, and I say, this tea cures colds.
And you've just fallen for the illusion of cause. This is a huge section in Dr. Beags' lecture. Our brains are basically pattern recognition machines that just never turn off.
The source material has some great examples. I drank turmeric tea, didn't get sick, so the tea must be some kind of magic shield.
Or the classic one about the full moon. More 911 calls happen during a full moon. Every ER nurse, every cop, they all swear it's true.
Is it not?
Statistically, no, it's an illusion. Think about it. When the moon is full and it's a crazy night at work, you notice the moon and you say, aha, I knew it.
But on a full moon night, when it's quiet,
You don't even think about it. You don't count the misses, you only count the hits.
it's confirmation bias.
It's even deeper than that, actually. Dr. Beags points to some evolutionary roots for this. Imagine you're one of our ancestors on the savannah. You hear a rustle in the tall grass, and then a lion jumps out and attacks your friend.
I'm right.
You're running. Now, the next day, you're walking by that same spot, and you hear another rustle in the grass. It's probably just the wind. But what does your brain scream at you?
It's a lion. Assume it's a lion, because if I assume it's the wind and I'm wrong...
You get eaten. We are literally the descendants of the paranoid ones. The people who assumed every rustle was a lion survived. The ones who waited for more data. Well, they didn't pass on their genes.
So we're just hardwired to be superstitious.
We're hardwired for false positives. We're biased to assume a pattern exists even when it doesn't. In the wild, that keeps you alive. In modern science, it creates dangerous myths.
And that's the perfect transition. Because sometimes these myths aren't just silly, like my lucky hat. Sometimes they are genuinely dangerous.
And this brings us to what is probably the darkest example in the lecture, the MMR vaccine and autism case study.
Right. It's so important to understand how this happened. It wasn't just people deciding to be anti-science for no reason. It started with one specific, very flawed paper.
The Wakefield paper from 1998. And Dr. Beags really takes it apart piece by piece.
It's a masterclass in how not to do science. First off, the sample size. How many kids were in this world-changing study?
It was 12. Is that right?
12. Just 12 children.
Yeah.
You cannot make a global claim about public health based on a sample of 12.
And it gets worse. He didn't find them randomly. He recruited them from his son's birthday party.
You're joking. A birthday party.
That's the level of scientific rigor we're dealing with here. Not to mention a massive conflict of interest. Wakefield was being paid by lawyers who were suing vaccine manufacturers.
Wow.
But the reason it stuck, the reason parents believed it, goes right back to that illusion of cause.
The timing.
It's all about the timing. This is the crucial point Dr. Beags makes. The signs of autism often become noticeable to parents around age 2 or 3. That's just the developmental window.
Which is exactly when kids get the MMR vaccine.
Right. So from a parent's perspective, you see event A, the vaccine, and then you see event B, the symptoms. Your brain screams, A caused B.
But it's just a coincidence, a collision of two different schedules.
Exactly. Without a comparison group, without looking at the thousands of unvaccinated kids to see if they also get diagnosed around age 2, you have nothing. You just have a story.
And when other scientists did do the real research, with proper groups.
Dr. Beags cites a huge one, H. et al. From 2019. They looked at, I think, over 657,000 children.
A little more than 12.
Just a bit. And they found absolutely zero association between the vaccine and autism. But the damage was already done. Because the illusion is so powerful and so intuitive, the math is not.
Yeah, that quote included in the notes from the ASD community really hit me. They said that reducing their lives to something to be feared and avoided is insulting and dangerous.
It really is. It shows the human cost of getting statistics wrong.
Okay, so we know our brains lie to us. We see lions where there's only wind. How do we fight back? How do we actually prove something is real and not just a coincidence?
And now, enter inferential statistics.
The heavy artillery.
This is the part of the course that students usually dread, but I think the logic behind it is actually beautiful. It starts with a very strange, very humble assumption.
What's that?
It starts by assuming that you are wrong. It assumes nothing is happening.
The null hypothesis.
The null hypothesis, or H0. It is the ultimate boring, pessimistic assumption. If you're testing a new drug, the null hypothesis says, this drug does nothing. Any difference you see is just random chance.
That feels so backward. Why do we start by assuming we failed?
Because it's really, really hard to prove something is true. But what you can do is prove that the nothing is happening idea is completely ridiculous. Our goal is to reject the null.
Okay, so we set up our boring null, the drug doesn't work, and then we have our exciting one, the alternative hypothesis. The drug does work.
Right. And Dr. Beags points out a little trap here that a lot of students fall into. It's about being directional versus non-directional.
Explain that.
Oh.
Because if I invent a drug, I'm going to predict it makes people better, not just different. That sounds like a direction to me.
It is, and it seems logical. A directional hypothesis says Group A will be better than Group B. But that's a really risky bet to make.
Why?
Because what if the drug actually makes people worse? What if it has some terrible side effect? You found a huge, important effect, but because you bet specifically on better, you technically have to say your hypothesis failed. You can't claim the finding.
You've painted yourself into a corner.
Completely. And that's why Dr. Beags advises, unless you have a really, really good reason, stick to a non-directional hypothesis. Just predict there will be a difference. Better, worse, you don't care. You just want to prove the null is wrong.
Okay, so we have our hypothesis. We've selected our data from the experiment. Now comes the big decision. Is our result real, or is it just dumb luck?
And this brings us to the concept that confuses everyone, the p-value.
The dreaded p-value. I swear, I have read the definition a dozen times. The probability of obtaining a result equal to or more extreme than what was observed, assuming the null hypothesis is true. It just sounds like legal gibberish.
It's so dense. Let's just use the coin toss analogy from the lecture. It's honestly the best way to get it.
Okay, so you hand me a coin, you say it's a fair coin?
That statement, the coin is fair, that's your null hypothesis.
Right, so I flip it 10 times, I get 5 heads, 5 tails.
Perfect. That's exactly what you'd expect. The null hypothesis is looking pretty good. You have no reason to doubt me.
Okay, but what if I flip it 10 times and get, say, 9 heads and 1 tail?
Yeah, you're starting to get suspicious, right?
Yeah.
Is it impossible to get that with a fair coin? No.
Yeah.
But it's pretty weird. It's unlikely. The probability of that happening by chance, the p-value, is very small. Maybe around 0.02.
A 2% chance. So I have a choice. Either I just witnessed a rare 2% event, or you lied to me and the coin is rigged.
That is the exact decision you have to make. And what if you flipped it 50 times and got 50 heads?
Okay, the coin is absolutely rigged. I am no longer believing your fair coin story.
You are rejecting the null hypothesis. The probability of that result happening by pure chance is so microscopically small that you are confident something else is going on. It's not luck.
So the p-value is just a weirdness score. The lower the p-value, the weirder my result is if the null hypothesis is actually true.
That's a fantastic way to put it. A low t-value is the data screaming at you, this is too weird to be an accident.
And in psychology, and for Dr. Beags' class, there's a specific line in the sand for what counts as too weird, isn't there?
Yes, the alpha level. And by convention, it's almost always set at 0.05.
So 5%.
5%. If the probability of your result happening by random luck is less than 5%, we call it statistically significant. We get to reject the null.
But Dr. Beags has a big warning in the notes about this number.
Right. It's arbitrary. There's nothing magical about 0.05. It's just a rule we all agreed to follow. And it leads to this weird situation where a result with a p-value of 0.049 is a breakthrough discovery.
And a p-value of 0.051 gets thrown in a drawer and forgotten.
Even though the actual difference in the data is tiny, and because we're still dealing with probabilities, not certainties, we can still be wrong.
Which leads us to the errors. Type I and Type 2. I always get these mixed up.
The fire alarm analogy Dr. Beags uses is the best way to remember it.
Okay, lay on me.
A type I error is a false positive. The fire alarm goes off, everyone panics and runs outside. But there was no fire. It was just steam from the shower.
So in science, that means I shout from the rooftops that my new drug works, but it actually doesn't. My result was just a fluke, part of that 5% chance.
Precisely. And we just accept that this is going to happen about 5% of the time we reject the null. It's the cost of doing business.
Okay, so then what's a Type 2 error?
That's the false negative. That's when the building is actually burning down, but the alarm stays silent.
So the drug did work, but my study was too weak to notice it. I missed a real effect.
You missed it. You failed to reject the null when you really should have. And preventing that all comes down to one key concept: power.
Statistical power.
It's the ability of your study to detect an effect if an effect is actually there to be found. And what's the easiest way to increase your power?
Get more mice.
Get more mice. A larger sample size, a huge sample size, is like a giant megaphone. It helps you hear a tiny whisper of an effect over all the random background noise.
So let me try to summarize where we are. We started with the idea that our brains are fundamentally liars. They see patterns everywhere, even when they're not real.
Lions in the grass. Right.
So to check ourselves, we invented this tool, inferential statistics. We start by assuming nothing is happening. That's the null.
The boring hypothesis.
And we only agree that something is happening if our data is so weird, so unlikely to happen by chance, that it passes that 5% threshold.
That is the core logic in a nutshell. We're trying to separate the signal from the noise.
But, and here's our cliffhanger for next time. We haven't actually done any of the math yet. We understand the why, but not the how.
That's part 2. Next time, the training wheels come off. We're diving into Z-scores, t-tests, and how you actually calculate that weirdness score.
And we're also going to look at another study on brain training. You know, do those apps and games actually make you smarter? Or is it just another illusion of cause?
Spoiler alert, it's complicated.
It always is. Now, before we wrap up, I want to go back to where we started. That lucky jersey.
Or my lucky coffee mug.
Right. We learned today that p less than 0.05 means we, as scientists, accept a 5% risk of being wrong. A 1 in 20 chance of a type I error, a false positive.
Right, that's the price of admission.
So think about that next time you're scrolling through your news feed.
Mhm.
If you read 20 different headlines this week about new studies finding that, I don't know, kale causes this or chocolate cures that,
Statistically speaking, one of those is probably a fluke.
it's just random noise dressed up as a scientific fact.
Look at your lucky jersey, by all means.
But maybe double check the headlines. Thanks for listening to The Deep Dive. We'll see you for part 2.